perhaps better for the camera or to have the lights on. I don't know.
Well, if I wasn't sitting here, you could move it this way and make it bigger.
Right. Well, we better get started.
The light curtains in the way of.
That one is in the way?
Yes.
Okay, I don't need it. First, a short summary of what we have done yesterday. Yesterday we have discussed homogeneity analysis. I want to emphasize once more that that is the same technique as multiple correspondence analysis. We first introduced the logical or qualitative concept of perfect quantification or perfect homogeneity. This was not very practical to work with. It was translated into matrix algebra in order to make it more practical, using the concept of an indicator matrix, which was defined. And it was made quantitative by using analysis of variance type terminology, between and within, correlation ratios, sums of squares, those concepts. Those concepts made it possible for us to define optimal homogeneity and optimal quantification instead of perfect homogeneity and perfect quantification. The technique associated with this definition of optimality was homogeneity analysis. Computations could be formulated as eigenproblems, eigenvalue, eigenvector problems, but we figured out that that was not a very good way of solving these problems because the matrices tended to be very big, and we used the least squares loss function in order to derive an alternating least squares algorithm. This alternating least squares algorithm worked by reciprocal averaging. Both geometrical and analytic or algebraic aspects of the technique were discussed. We both had pictures of loss, and we translated the technique into properties of the correlation matrix that were optimized. So that is a short summary of the main things we did yesterday. I'll now proceed with showing you some gauges for multiple correspondence analysis, again as illustrations of the type of data matrices that you can apply the technique to. This is from the book by Meulman, which is in your list. And it's a random sample of size, well, let's say 40, from a multinormal distribution, an equicorrelated multinormal distribution. All the correlations between the variables are equal to 0.95, and there are 7 variables. Of course, it's not directly a random sample from a multivariate normal distribution because there are integers there. So the observations were subsequently categorized into 5 categories. Now, this is what you get. This is such a data matrix you get by this operation. And we're using this gauge because this is a matrix of which we know a great deal. We know that it comes from a multinormal distribution. We know the discretization rule. We know the number of categories. We even know the intercorrelation of the variables. And this is one of the representations you can get from one-dimensional homogeneity analysis. Now what we did here is we made this data matrix that I just showed you, which was a 40 times 7 data matrix, into a 40 times 35 indicator matrix. 35 because 7 times 5 is 35. And there were 5 categories for each variable. So you have 7 indicator matrices of 40 times 5, and you put them next to each other. And then you perform your homogeneity analysis, and after you've in one dimension. And after you've done that, you reorder the rows of the matrix and the columns of the matrix using the scores for the rows and the columns that come out of the homogeneity analysis. And you get this nicely banded structure, which is already quite familiar perhaps because it also occurred in the Münzinger Rhine archaeological example yesterday. So this is one way of presenting the results of one-dimensional homogeneity analysis, and it also shows you that homogeneity analysis can be used to look for these parallelogram structures, as they are often called. This is another recent paper by, from a recent paper by De Gruyter. That's a Dutch name. It's in one of the 1985 issues of Applied Psychological Measurement. And he uses homogeneity analysis on data generated by the Birnbaum three-parameter logistic model. And this three-parameter logistic model of Birnbaum has, among other things, discrimination value parameters, which show you how these item characteristic functions increase, how fast they increase. And De Gruyter compares the theoretical discrimination measures, which are given, in this sense this is a gauge again. He compares them with the recovered discrimination measures found by homogeneity analysis, and he discusses the nature of the recovery and the distortions that you get from using homogeneity analysis on examples of this type. So if you're interested in test theory and want to find out what homogeneity analysis does with typical test data, then perhaps this is a place to look. Another example of gauging, because the data were generated by a well-defined model of which you know all the properties. Here's another one. There was a question yesterday whether homogeneity analysis or this type of optimal scaling was related to the Goodman scale in one way or another. And it's related in various ways. The first and most obvious way is that homogeneity analysis was invented by Goodman in 1941. And Goodman scaling was invented by Goodman in 1940. So that's a very close relationship. And as a matter of fact, they were invented more or less for the same purpose, for scaling qualitative variables, for constructing a scale from measurements on a number of qualitative variables. And this technique is known as the principal components of scale analysis and has been presented as such by Goodman in 1941, and more specifically by Goodman in 1950 in a paper in Measurement and Prediction, the American Soldier volumes, volume 4, in which he works out very much in detail what happens if you apply homogeneity analysis to data that have been generated by a perfect scale, by a perfect Goodman scale. So this is another early example of gauging of the technique of homogeneity analysis. What happens if you apply it to a perfect scale? Well, what happens is shown in the plots here. I've taken a number of Goodman items with varying degrees of difficulty. Increasing difficulty, this is the difficulty given here in the first plot. And I've plotted the eigenvalues of the eigenvectors that come out against the difficulty rank number on the x-axis. So the first eigenvalue is a decreasing function of difficulty. Could also be made increasing again, of course. The second eigenvector is a quadratic type function of difficulty. The third one is cubic. The fourth one is quartic, and so on and so forth. You can say much more precise things about them, which I will not do because they're in the Goodman paper. I've also drawn in by hand the the x-axis in the first 4 plots of the eigenvectors at least. And you see that the number of crossings of the axis increases by 1. There's only 1 crossing in the first one here. There are 2 crossings here, 3 crossings of the axis there, and 4 crossings there. And that goes on like this. So this is a distinctive property of the Goodman scale. It's even, this is going to be very dangerous in the long run. Perhaps, yes. Every little bit helps. Yes. There's even more stronger property. This root here, this crossing, is between the 2 here. These 2 here are between those 3 here. And these 3 crossings are between those 4 crossings here. So the crossings are, not only do they increase in number, but they're also interlaced in that sense. You can find these properties, among other things, in the paper by Goodman. There are also references in the book by Gifi to much earlier mathematical literature where these results are proved. So this is another example of gauging of homogeneity analysis in which we apply it to a data set with known properties. Now I'm running a little late in terms of the program that was distributed at the beginning of the seminar. This shouldn't really worry you, because the more you discuss with the general principles, the easier it becomes to discuss the specific cases. And I think I should have talked about correspondence analysis yesterday, correspondence analysis proper. So not multiple correspondence analysis, but correspondence analysis proper. And we will now get to correspondence analysis proper, so in a sense I'm running an hour late, but since we have already discussed multiple correspondence analysis, we can be relatively brief about correspondence analysis. First, some historical remarks. Who invented correspondence analysis? There are some conflicting ideas about that, but as far as I can tell, the first real reference was a paper by Hirschfeld, who was later immigrated to the United States and became much more well known under the name of Hartley. It was written in 1935 in Proceedings of the Cambridge Society. It was written when he was still in England and just had come from Germany. There's another sort of influential paper by Fisher, R.A. Fisher, in 1941, in which some form of correspondence analysis is described. There is multiple correspondence analysis, which was described by Goodman in 1941, as I pointed out. And the first real application of correspondence analysis was perhaps by Kind Maum of the Galton Laboratory to the study of eye color and hair color and their relationship in a very large sample of Scottish school children. The technique is known under even more different names than multiple correspondence analysis. It's also known under a name which are Hayashi's nth method of quantification. The previous one was the nth method. I always forget the numbers, but Hayashi popularized the method in Japan, and there are many applications of it in Japan since the early 50s. There's a canonical analysis of contingency tables. This is the name used, for instance, in the Kendall and Stewart books, Advanced Theory of Statistics, the chapter on the analysis of categorical data. And I think the ecologists use yet another term which has to do with this reciprocal averaging algorithm. So again, there are many different names for the same technique, and the technique is still being rediscovered by people in various fields who propose it as if it was something completely new, which is sort of strange because it has been around for at least 50 years. And there are even traces of the technique in a paper by Carl Pearson, which was written in 1905. So it's not really a new technique that I'm going to be talking about today. Well, the first and most obvious way, given the fact that we've already discussed multiple correspondence analysis, the first and most obvious way to introduce it is to say correspondence analysis is multiple correspondence analysis for the case in which there are only two variables. That's brief and succinct, and it's completely true. And having said that, we could perhaps proceed and go on with the next topic. But there's more which can be said about it, obviously, otherwise it wouldn't be such a popular technique. This is perhaps a bit too brief, it says here, yes. And the reason why it's a bit too brief is that correspondence analysis can be derived in many different ways. There are many different ideas which, let's say, qualitative ideas which ultimately lead to the equations defining correspondence analysis. The same thing is true for principal component analysis type of techniques in general. There are many different qualitative ideas which, when translated into mathematics and to matrix algebra, eventually lead to principal components. But the fact there are so many different qualitative ideas partly explains the fact that the techniques are discovered over and over again. There are many entrances, many different ways in which you can reach these equations. In France, for instance, the technique is very popular and it's presented in many different ways, and usually not as a special case of multiple correspondence analysis. In fact, in France, multiple correspondence analysis is usually presented as a special case of correspondence analysis. So this is to increase the confusion. I will first give the regular French way of discussing correspondence analysis taken directly from the works of Ben-Zachary. And for that occasion I will change my notation a little bit. So if you see an n somewhere, it's not necessarily the same n as the n you saw before. Correspondence analysis is devised for frequency tables, or for tables with probabilities, or for tables with relative frequencies, n times n tables, tables with n rows and m columns, which are filled with numbers. You very often see it applied, especially in France, also to other tables with positive numbers, which are not necessarily frequencies. They could even be things like distances or something like that. But the technique is far less natural for such tables, for reasons which I hope will become clear during this presentation. So let us define such a table. F, it's a frequency table, and for convenience I've made it a relative frequency table. That is, I've divided everything by the grand total, so that these numbers all add up to 1. And I'm defining E and D, which are the two vectors with marginal frequencies of the bivariate distribution, or the cross table, or the contingency table. These are all names that you can use for such a table. Now Ben-Zachary starts by defining a particular distance measure on the rows of this table. This distance measure is supposed to tell you how dissimilar these rows are. And I've written it down. I call it the Ben-Zachary distances. Ben-Zachary doesn't call it the Ben-Zachary distances. He calls it the chi-square distances, but I think it's nice to call them Ben-Zachary distances. Well, he could hardly do that himself, of course. So,
You call them DeLeo distances.
he could call them DeLeo distances, yes. Well, I have to talk to him about that. Well, anyway, this is the way they are defined. First you make the row I and row K into a profile, as it's called in French and in English, by dividing by the corresponding marginal total. And then you take the sum of squares of the differences and you weight by the inverse of the column sum, and you add the whole thing, and then you have the Ben-Zakri distance. This is related in a sort of obvious way to the chi-square for independence, because the chi-square for independence also takes the elements of the frequency table and corrects for the marginals in some way or another. The precise relationship will be given below, I think. And here is the matrix notation for the thing up there. I'm using U for a unit vector. A unit vector is a vector with all elements equal to 0 except 1, which is equal to 1. And Ui means that element I is equal to 1. Uk means that element k is equal to 1. So this is really only another way of writing down the same equation up there. E and D are now diagonal matrices. They used to be vectors, but now I've collected these vector elements in the diagonals of a diagonal matrix. Now the idea of correspondence analysis as presented here, or as presented by Ben-Zakri, is to approximate the Ben-Zakri distances by ordinary Euclidean distances. So what you want to do is you want to make a picture again, and in that picture each column or each row, I'm scaling rows here, each row will be presented by a point. And again, this could be a one-dimensional picture, a two-dimensional picture, and so on, but I'm not specifying that directly. You're trying to make a picture, and you represent row by points in such a way that the distance, the ordinary distance between the row points, is approximately equal to the Ben-Zakri distance between these rows. In order to do this properly, we use the singular value decomposition. I'm more or less assuming that you're familiar with the singular value decomposition. I don't know how safe that is, but this is a given matrix. This is the matrix of frequencies corrected for the marginals. And this is the singular value decomposition of this matrix. There's a square orthonormal matrix on the left, a square orthonormal matrix on the right, and a diagonal matrix with positive or at least non-negative values in the middle. Now, what I just said is not exactly correct if this is not a square matrix, but then you have some zeros instead of a true diagonal matrix. And you define, using this singular value decomposition, you define x, and this x is supposed to give you the scaling of the rows that you're looking for. Now, if you substitute x into this expression up here, then you will find that indeed the ordinary Euclidean distances between the rows of x are equal to the Ben-Zakri distances between the rows of f. So you have attained what you have set out to attain. You have made a picture in which Ben-Zakri distances are represented faithfully. And of course it's not specified here how many dimensions this picture has, because it's not specified here what the rank of this matrix F is, or what the number of non-zero singular values is. Usually there will be too many non-zero singular values for a convenient picture, and in that case of course you use a truncated singular value decomposition. You throw away some of the smaller singular values. If you have a truncated singular value decomposition in p dimensions, a little bit lower perhaps, then you have a relationship, a chain of inequalities, which is listed up there. x1 is now the representation in one dimension, corresponding with the largest singular value. x2 is the representation in two dimension, corresponding with the two largest singular values, and so on. And you have this nice chain of inequalities which shows that you approximate the Ben-Zakri distances from below. You're always short. Ben-Zakri distance is always larger than the Euclidean distance in your picture, unless you have happened to hit the correct rank. In that case it's equal. I have an example which shows that in a sort of relatively clear way. The example is perhaps not very clear for you, but you could easily substitute an American example. This is Dutch elections. And the numbers here are districts of the city of Leiden. And the labels, which are not numbers, the letters, are Dutch political parties. We are in the, for people involved in multivariate analysis and multidimensional scaling, we are in the fortunate situation that there are about 15 Dutch political parties in parliament. And that makes interesting examples. If you're only two parties, of course, you can forget it. I'm not presenting this as an argument for the Dutch system, but it's very convenient for our purposes. So there are a couple of Dutch political parties here which I could identify. This is the left, links means left. This is the right. And these are really the extremist parties. These are the Social Democrats. These are the liberals, and liberals is not meant the same way as liberals is meant over here, but it's meant in the sense of conservatives. I can't help that. It's old-fashioned 19th century laissez-faire liberalism. And over here are the Social Democrats. It's the largest party in Leiden. PVDA, yeah, that's the Workers' Party. And there are also two labels here which I have not explained yet. This one is people who gave a vote which could not be counted because it was invalid for some reason or another. And this is the number of people who were not there at the election. I mean, all the voters are registered, so you can also vote who wasn't there. There's also D66, which is a party I'm not going to... Well, it's comparable to the third party in England, the coalition, as it's called, of Social Democrats and liberals again. So this is this is a short course in the Dutch political system, which is in itself not interesting enough to go into in great detail, but I can use this example to show you the approximation of the Ben-Zakri distances. Here you have on the x-axis the distances as computed in the picture, and on the y-axis you have the Ben-Zakri distances as computed directly from the table. And you see that the Ben-Zakri distances are always underestimated. This is in a one-dimensional representation, so it's not the one I just showed you, which was two-dimensional obviously. This is in a one-dimensional representation. You see a lot of underestimation. And not surprisingly, a similar plot for the two-dimensional representation already looks much nicer. So here you have the approximation of the Ben-Zakri distances by the Euclidean distances in this two-dimensional plot that I just showed you. They're labeled in terms of pairs of political parties, of course. So this is the left and the Christian Democrats. This distance which is approximated quite nicely. And there are also some distances which are still underestimated quite severely. So you could look at that. These are sort of residual plots. Right. Not surprisingly, yes?
What information do you get from comparing the distance from the 45-degree line? What does it say when one is a lot further than the others? What does that say about the data?
Well, this 45-degree line is exact fit, which means that if something is here, it has a large distance in the data. It's large on the data scale. This is the data scale of distances to the y-axis. And over here you have the x-axis, that's the representation, the distance scale for the representation. So the distance to the 45-degree line tells you something about the fit, but the location of the point on either the x-axis or the y-axis tells you something about the distance in the data or the distance in the representation. So it is just, it's an somewhat peculiar way of plotting distances. You usually only connect these points or something like that, but here, to illustrate the fact that you're underestimating, you have drawn these lines here. So what it tells you about the data is that the distance between V and S is very large, and it also tells you about the approximation, that it's approximated quite well, and that it's also a very large distance in the plot that I just showed you. That's what's given in this plot here. Both information about the size of the distance in the data, the size of the distance in the representation, and the degree of approximation. Yes?
How about if you brought it back to the example, what would you learn from looking at this in terms of the example?
Well, in terms of the example, you would have a concise summary of, let's say, the correspondence between districts in the city of Leiden and voting pattern in these districts. You could see that a particular district had high representation of, well, not a high representation, must be careful with the formulation, but higher than expected representation of democratic Christian Democrats, and a lower than expected representation of Social Democrats, for instance. These relations should be apparent from the plot, because what you're actually measuring, of course, is the departure from the independence hypothesis, departure from what you really expect. You're correcting the matrix for the product of its marginals. I'll come to that a little bit later. Interpretation in terms of chi-square and in terms of independence. But on the other, this is simply, if presented in this way, and that's the way Ben-Zakri presented it, and the reason why he was invited to come to Bell Telephone Laboratories. If you present correspondence analysis in this way, it's simply a form of multidimensional scaling. It's you have distances, derived distances from your data, which you try to approximate in a low-dimensional representation. So in this sense, I'm talking about multidimensional scaling now.
The plot only has parties in it?
This is only approximation of distances between parties.
I mean, the previous plot only has party points?
No, this also has 57 districts in it.
Okay. So what are those? There's some sort of weighted centroid relationship in here?
Well, this is a symmetric representation, the biplot representation. So there's no centroid, there's a, let's say, an inner product relationship between the two sets of points. Back to this one.
Is basically the same as the biplot of Gabriel?
This is one form of the biplot of Gabriel. You can of course apply the biplot technique to any square table, and this is a particular application to frequency tables. But the basic relationship, well, actually this part in red is it's a biplot Gabriel here, so you're right on time. One of the ways in which you can write the singular value decomposition is in this, in the way in red here, x and y. This is simply the singular value decomposition again, perhaps a little bit in disguise. There are two parameters here, alpha and beta. And there are several choices possible for alpha and beta. If you choose alpha equal to 0, in other words, if you do not include anything, no singular value contribution in the first equation, and beta equal to 1, this one is up here, then you're using the first centroid principle. Now that means that the x's are weighted averages of the y's, but the y's are not weighted averages of the x's. Again, this is what we also talked about yesterday in connection with multiple correspondence analysis, you cannot have both centroid principles unless the singular values are all equal to 1, but that of course is highly unlikely. The other way around, you have the second singular value decomposition, the second centroid principle. If you distribute it equally over both equations, you have alpha equal to 1/2 and beta equal to 1/2, then you have the biplot scaling, which is similar to what Gabriel would probably do in this context. Now, if you have the biplot scaling, you have none of the two centroid principles. This is important to remember. Neither the rows are in the weighted average of the columns, nor are the columns weighted averages of the rows. But what you do have is this biplot interpretation, which, well, I'm not going to elaborate on it, but it means that the inner product of the two vectors, of a row vector and a column vector, approximates the element of the original data matrix. So there's an inner product type of approximation if you use this particular type of scaling. And if you use both alpha and beta equal to 1, then you have what I call here the French scaling. This is what most of the French do. And unfortunately, in the French scaling, you have none of the two centroid principles. You also have not the inner product relationships familiar from biplot. The only thing you have is approximation of the Benz-Decree distances within the rows and approximation of the Benz-Decree distances between columns. Between rows and between columns, but there's no relationship between row elements and column elements. So this scaling does have some disadvantages. Again, this is all singular value decomposition in disguise with different types of normalization.
With the other kinds of normalizations, do you have the same within, say, rows interpretation?
Well, the problem is that you would like, in a joint plot, you would like to have some relationship between the columns, or between the points presenting rows and the points representing columns. Now, this relationship can be either the centroid principle or the inner product relationship. Now, in order to have that, you must have that alpha and beta must add to 1. That's basically the relationship that you need.
Yeah, that's not what I was asking. I was asking about the within rows or within column interpretation.
Yes.
In the French case.
Yes.
Is that also the case for the other?
No, only if the corresponding parameter is actually equal to 1, which means that you cannot have it both ways again. So here, for instance, if you use the first centroid principle, then you're approximating Benz-Decree distances of the y's and not of the x's. And the other way around is the other way around. So you have to choose what you want, whether you want to approximate these distances, whether you want to approximate inner products, or whether you are very fond of the centroid principle. I shall briefly show you this transparency again. This is the multivariate analysis books, of course. Our early application of correspondence analysis. And this illustrates one of the centroid principles, because now the books are in the centroids of the topics. I've scaled them in such a way that the books are in the centroid of the topics, which means a particular choice for this alpha and beta scaling parameter. That means, of course, that the set of books is in the convex hull of the set of topics. And in this case, the convex hull of the set of topics is this equilateral triangle that we talked about. So topics are on the outside, books are on the inside. This is one of the consequences of the centroid principle. If the singular values are very low, it means that the centroids will all be very close to the origin, and you have not a very nice plot. Here the singular values are quite large, and it's not so that all the books are somewhere there. So this is another form of scaling, as it were. Briefly, the relationship with multiple correspondence analysis, more in detail. multiple correspondence analysis, we first construct the birth table for two variables. In order to construct the birth table for two variables, you only have to use these four different subtables. F, which is the contingency table that we were analyzing, and E and D, which are the two diagonal matrices of marginals. Now, the eigenequation for multiple correspondence analysis, which is written on top here, can be simplified directly to this singular value equation for ordinary correspondence analysis. That's very simple to do. So it shows that there's a very simple relation between the two techniques, and that the relation between the singular values of correspondence analysis that we talked about and the eigenvalues of multiple correspondence analysis is given by this relation in brackets here. It's a linear relationship. This also explains why multiple correspondence analysis has n plus m eigenvalues, and of course ordinary correspondence analysis only has minimum nm singular values. Where do the extra eigenvalues come from? And the extra eigenvalues come from the fact that the solutions occur in pairs, that each singular value creates two eigenvalues, one given by the relation up there and the other given by the relation down there. And if m is not equal to n, then you have a number of trivial eigenvalues given by 1/2 basically. Now this shows that correspondence analysis is a very simple special case of multiple correspondence analysis. As I have said in the beginning, the French do it the other way around. The French emphasize the fact that multiple correspondence analysis is correspondence analysis applied to the indicator matrix. So if you use the indicator matrix that we have used to define multiple correspondence analysis, and this indicator matrix consists of a number of indicator matrices for each variable next to each other. If you apply correspondence analysis, ordinary correspondence analysis to that indicator matrix, then you get exactly the same results as you would get from multiple correspondence analysis. Now this shows that multiple correspondence analysis is a special case of correspondence analysis. And this remains true if G is incomplete. Then you can also apply multiple correspondence analysis to this, ordinary correspondence analysis to this indicator matrix, and you get the same results as you would get from homogeneity analysis with missing data deleted. So that's another important relationship between the two techniques. There's a third relationship. The third relationship is if you apply ordinary correspondence analysis to the birth table, then you also get the same results as you would get from multiple correspondence analysis. So also in that sense, multiple correspondence analysis is a special case of ordinary correspondence analysis. All this, well, it's not very important, of course, which is a special case of which. It's just important that you can look at the techniques in these various different ways. There are some relationships for ordinary correspondence analysis which carry over from relationships we have already discussed for multiple correspondence analysis. The first one is the relationship with chi-square. The sum of squares of the singular values is equal to this chi-square of the contingency table. This is something which has been discovered a very long time ago. It's very prominent in the work of Lancaster, for instance. It's also very prominent in this chapter of the Kennel and Stewart book that I've talked about. Sum of squares of the singular values is equal to the chi-square for independence. As a consequence, it's possible to think of correspondence analysis as a technique which decomposes departures of independence, which analyzes the residuals of the independence model. So you fit an independence model to your contingency table. This gives you residuals. For most interesting data sets, will give you residuals. How can you make a picture, or how can you get a quick impression of what the residuals, what structure there is in residuals? Answer, apply correspondence analysis. There's a recent paper, very recent actually, because it's not out yet. In the December issue of Psychometrica, there will be a paper by Peter van der Heijden and myself on using correspondence analysis complementary to log linear analysis. And that basically means using correspondence analysis as a technique to analyze the residuals of a log linear analysis. There are a number of other papers by the same authors which are probably referenced in that paper, so I will not mention them here, but the general idea there is the same. I'll probably come back to that later. Another interpretation of correspondence analysis is that it is a technique which maximizes the correlation between all possible correlations that you can compute from a contingency table by assigning scores to rows and columns. That was a very long sentence. If you assign scores to the rows of a contingency table and to the columns, then you can compute a correlation coefficient. Different scores will lead to different correlation coefficients. What are the scores that lead to the largest one? These are exactly given by the first dimension of correspondence analysis. So correspondence analysis gives you the maximum possible correlation. In that context, it was almost discovered by Carl Pearson in 1905. This makes correspondence analysis perhaps interesting as a scaling technique. Find a scale from a table of, for instance, this is a table taken from the book by Guilford. Psychophysical data, spotted patterns which had to be ordered in a number of categories at equal appearing intervals, as the phrase is. And if you group the judgments of all these subjects, then you have this is the number of spots on the card. This is the number of the interval in which the card is placed. The data, I think, described a bit more in detail in the list of possible data structures. I think, I hope, I expect. Again, you can apply correspondence analysis to this table, and it is clear already from the way the table looks that correspondence analysis will work very well because the diagonal structure is already there without any rearrangement at all. And these are the transformations of the row and column categories that you find. And of course, you can use the transformation of the spot patterns, the stimuli, as a scale for those stimuli. This scale has certain optimality properties. Again, this is not a new application of the technique. It was also already outlined by Goodman in 1946 in a paper in the Annals of Mathematical Statistics. He applied it to paired comparisons data, but you might apply this as well to these equal appearing interval data or any type of psychophysical scaling data. This is a transformation that the technique finds for the categories, and that sure looks familiar. So this is another application of correspondence analysis to psychophysical type of data. And you can use it to construct a scale. There's another way in which correspondence analysis can be derived. That's the way it was derived by Hirschfeld-Hartley in 1935. Correspondence analysis linearizes the regressions between the row and column variable. Now again, this is the singular value decomposition in disguise that I'm mentioning here. To make this clear, if you just forget about these contributions of the singular values at the end, then what is stated here, the centroid, the average, is of course a conditional expectation. It's the average of the column variable for each value of the row variable. So this is a conditional expectation, and the fact that these rows are there means that the conditional expectations with this particular scoring system are linear, and consequently correspondence analysis linearizes the regression. Both the first set of scores gives you linear regressions, the second set of scores give you linear regressions, and so on and so forth. That was the way in which the technique was discovered by Hirschfeld, because he wondered whether it was always possible to find a system of scores which linearized the regressions. It was also, again, one of the ways in which Carl Pearson almost discovered the technique. I have to put this in its right place. Let me see. Oh, here, yes. Correspondence analysis linearizes the regressions. Here's an example of this. This is ordinary contingency table crossing two variables. The first variable is the school, the type of school that a person went to. This is a sample of approximately 30,000 soldiers, or people who wanted to become a soldier. No, that's not the correct expression. People who had to become a soldier and were consequently forced to take a psychological test. And was also asked what kind of schooling they had. This kind of schooling they had is on the y-axis the results of the psychological test, which is a shortened version of the Raven. Intelligence test is on the x-axis. The entries of the table are listed, are used as labels, so you can actually see what the table looked like. But the spacing we have chosen for the tests and the schooling labels on the y-axis and the x-axis is dictated by correspondence analysis. Now, if you use this particular spacing of the labels, then the regressions come out precisely linear. So this is one convenient way to represent a contingency table. It gives all the information you already had, the table itself, because it's in the picture. It also gives the maximum correlation, because the maximum correlation, of course, is the angle between the two regression vectors, two regression lines. And it also gives the correspondence analysis scores, because they're reflected in the spacing of the variable on the x and the y-axis. So this is one nice way in which you can present at least one dimension of a correspondence analysis. You can also present the second dimension in this way, but then you have to do it all over again. Of course, you get a second picture, because the spacing will differ for the second dimension. So this is the regression linearizing property, which is also quite convenient and important. Sort of mix up here. The final property of correspondence analysis that I would want to show you is the Fisher decomposition of a contingency table. You could also call it the Fisher-Lancaster decomposition, because it's also been studied in great detail by H.O. Lancaster. Fisher derived it in 1941. It's not actually in his paper of 1941, but it is in the paper by Kind-Maun, in which the technique is applied to the eye collars and hair collars. And the Fisher decomposition of a contingency table, again, is the singular value decomposition in disguise. This is the original table. These are the marginals, D and E. And this is the decomposition of the residuals after you have fit the independence model, as it were. Same rows and scores, row scores and column scores occur here, and singular values as in the singular value decomposition. So any table of any form whatsoever can be written in this particular form if you take enough of these components, of course. The number of components should be equal to the rank of the matrix. If you take fewer, then this, of course, is a restrictive model, which can be tested if you want to, but not with correspondence analysis. Now, it's clear, I think, from this presentation that correspondence analysis is a technique which is meant primarily for two-dimensional tables. But if you have more than two tables, you can, of more than two-dimensional tables, two variables. If you have more than two variables, you can still do a number of things. One thing, of course, is to apply multiple correspondence analysis. And we have seen that multiple correspondence analysis is the same thing as correspondence analysis either on the indicator matrices or correspondence analysis on the bird table. Another thing which you can do is to apply correspondence analysis to compound tables. And compound tables are tables that you get from multidimensional tables, multidimensional frequency tables, multidimensional contingency tables by stacking them on top of each other in particular ways. This is a nice example from the Dutch Central Bureau of Statistics. I don't know if it's readable, but from here it's nice. These are persons who are suspected of shoplifting by age and sex and by the kind of goods they have stolen. And the age and sex, of course, is men and women, and the age classes are listed here. The type of goods they have stolen are on top here. Clothing, provisions, tobacco, books, records, household goods, sweets, toys, and so on and so forth. Now this is, of course, really a three-dimensional table. You have age, you have sex, and you have the type of good that was stolen or that the person was suspected of having stolen. But you can pretend that it is a two-dimensional table by simply stacking the two, as is done here, on top of each other. Another way of formulating this, by the way, is that you treat age and sex as one single interactive variable. So you do not have two variables with respectively 2 and 9 categories, but you have one single variable with 18 categories. Women between 15 and 17 and men between 18 and 20 would be typical categories then. Now here's the joint correspondence analysis plot that the Central Bureau of Statistics derived from this table. There's a solid line connecting the men points, and there's a dotted line connecting the women points in order of age. And you find that young people steal comparatively more toys and sweets, especially young men, and that clothing is stolen considerably more by women in the middle age classes. Perfumes also, also not surprising. Hobbies, tools, records are stolen by older men. Tobacco stolen by younger men. And, well, there are various interesting relationships, some of which are immediately apparent from the table, but this picture, do not forget it, explains more than 90% of the chi-square that is already in the table, and it explains the residuals of the departure from independence, of course.
On that example,
Yeah?
you pointed out that you collapsed 3 to 2 variables.
Yes?
You also could collapse that to 1 variable just by stacking everything on top of one another. Would that change the outcome?
It would, well, again, you can stack that on top, or you can collapse that in different ways. You can add it over sex, or you can add it over age. And that would give, again, you're anticipating on my next example, that would give different results in general. And you can see here that, for instance, if you collapse over sex, you can more or less see what happens. This age curve is roughly the same for both sexes. So that will occur, but it will be in the middle of the two age curves.
I meant that you keep the sexes distinct.
Yeah.
Just create everything with one tremendously long column. Just doing what you did for sex and age, but doing it also for the type of crime, just putting everything all on top of one another.
So you have a one-way table.
One-way tables are not used in multivariate analysis in general, I would say. You cannot apply correspondence analysis to a one-way table. Well, you can, but maximal correlation is always equal to 1, and chi-square is always equal to 0, and so there's nothing left for correspondence analysis to work on. If you take out the marginals of a one-dimensional table, nothing's left.
And how would this change if you had a three-way table? If you did not collapse the sex and the age together?
This is a three-way table, originally. I mean, it was intended to be.
You emphasize that you collapse sex and age into one variable, to be considered as one variable between the columns.
Yes, but this collapsing is not really collapsing. I have two variables, two values for sex and 9 values for age, and I create a new variable with 18 values. So I haven't collapsed anything in any sense of the word. There's no information lost.
So the solution would be the same if you put male and female up at the top and divided, instead of combining the age and sex, you combine the type of...
No, solution would not be the same. You would be studying the departures from a different independence model. Yes.
If you did this as multiple correspondence with a three-way table,
Again, something different would come out. Yes. Because again, you will be studying departures from another type of independence. These are some...
2 sex points and 9 age points instead of 18 age sex points.
This is from the Van der Heijden and de Leeuw paper, which will come out in Psychometrica in December. It's suicide data. I would never have selected this, but my first author is the generation of the 80s, and he's selected the suicide data as an example. It's German suicide data from the German Central Bureau of Statistics. It gives you a three-dimensional table, sex and age by method of suicide. There's some very gory methods in the list there. You can probably look at them. Now, this paper in particular, and the analysis that I'll show you are taken from that paper again, show that it makes a difference how you analyze such a three-dimensional table. Whether you take, let's say, the table for males and the table for females and put them on top of each other, or whether you take a table for each age group and put them on top of each other. Now, this is the table in which method is used for the rows and sex times age is used for the columns. This is very similar to the shoplifting data, in other words, because we also have an interactive sex and age variable, and you have the other variable is the variable which is the other mode of the two-way table. Now, these are again the curves for men and women, which look very similar, but which are still in different regions of the space. And the ages are grouped along this curve in some sort of, well, they're not spread in different ways. It's still possible to draw a contiguous curve through them, so they're ordered along that curve. I will not go into the details of the solution, but they're described in considerable detail in the paper, I would say. The thing that I do want to show is that if you take another, well, there's something in red below which is interesting. That's the log linear model which you're decomposing the residuals of. So the log linear model is the model which says that method is independent of sex and age taken together. And That model doesn't fit very well, so there's something left for correspondence analysis to work on. And that what is left for correspondence analysis to work on is decomposed in these two dimensions here. The total chi-square that is left after fitting this model is explained, and I'm using that word, of course, metaphorically, by this picture here for 52%. Oh, no, not for 52%, I'm sorry, for 90%. The numbers in brackets here must be added. I mean, the first dimension, 52, the second one, 38. This is another log linear model which is studied. Consequently, there's another way in which these tables are stacked on top of each other. We have now taken age as a variable defining the rows, say, and we have taken an interactive variable of method and sex. So you now have, let's say, women hanging, men hanging, women jumping, and men jumping, a variable with categories like that. And this is the picture that comes out, which is still has this age curve here, but which is now quite different in terms of conclusions. It also explains about 90% of the chi-square residuals. And I don't really know enough about these data to show you what the exact outcome of the analysis is. But the point I'm trying to make is that it is important to choose, if you want to use these compound tables, to choose a particular way of stacking the variables on top of each other, the tables on top of each other, particular way of coding. And you can do that, for instance, by looking at the corresponding log linear model and trying to find out which one makes sense and which one does not make sense.
And really out of time. Breaking point.
Yes, I think this is a nice point to break.